Hi YouTubers, and welcome to this next in the electronics tutorial series where we're going to be looking at capacitors. Now, capacitors come in all shapes and sizes. They come from kind of these smaller ones, these electrolytic, although electrolytic certainly aren't the smallest. You've got ceramic, tantalum. In fact, you probably can't even see that little small one over there. And then we obviously get to the bigger beasts like this one over here, which is a supercapacitor. And then we get to kind of big filtering capacitors, which can be on mains, electricity power supplies. Now, in this tutorial, what I aim to do is, for one, just to give you a nice general introduction to capacitors, explain what they are, how they work, and how they can be applied in electronics. We're going to talk about how to choose a capacitor, safety around capacitors, and then the future of capacitors. So we're going to certainly have a little bit of theory. I've got a nice analogy laid out on the bench, which will hopefully help you understand the way they work in terms of how they operate with DC and AC and reactive frequency. We're going to have a practical demonstration as well. So this video might be fairly drawn out, so I'll probably break it into two parts, a part one and a part two, so I can complete everything. Right, so let's just talk about briefly what a capacitor is. Now, a capacitor, the very simple basic term of a capacitor is that it's like a little battery. Although it's got some wonderful characteristics which make it far better than a battery in terms of electronics use. A capacitor is basically a device which has got two plates with an electrostatic charge on either side of the plates. And due to that electrostatic charge, you can have an induced current. And that's how you get your charge build up. You can get a charge build up in the plates, and then you can get current flow. Now, I said we've got a nice analogy to hopefully give you an understanding, because when I say current flow, current doesn't actually flow through the capacitor. But for conventional understanding and conventional use in electronics, we assume that there's current flow, although that doesn't actually happen. But the analogy should explain that. Now, your capacitor, the plus sides of a capacitor compared to, let's say, a battery, is that you can charge it very quickly for the most part, depending on the type of capacitor, and you can discharge it very quickly, which is a property that a battery doesn't have. And when we talk about the future of supercapacitors, that potentially becomes very interesting, and that I'll talk about at the end of the video. Right now, let's get down to the bench. Right, so in preparing for this tutorial, I realized that even though the capacitor may seem like a very simple device, there's a fair bit to cover off in terms of electronics and the role that it actually plays. Although it seems perhaps like a very simple component, it actually does play a fairly critical role in leading us into digital electronics as well. Now, as I said, you get capacitors of all types. I said this is an electrolytic, and inside the electrolytic you're going to have paper that's coiled up as a dielectric to separate the plates, and potentially a wax or some fluid in there, and that we'll talk about is potentially an issue, and why that in particularly power supplies and electronics, capacitors can be the downfall, because they are one of the key pieces to look at in terms of fault finding, because they can fail relatively easily. Then we're going to say we will talk about the supercapacitors and the role they play in the future. And over here, when I start going into the kind of theory, I've got this nice old variable capacitor, which at least lets us have a look inside at very basically the construction of a capacitor and how it works. And this we're also going to demonstrate on the oscilloscope. What I'm also going to talk about at the end of the video, which I want to lead into just to make you aware of, is that potentially there are loads of different kinds of tools. The most common tool you'd think of using for kind of working with capacitors is a standard multimeter. You can measure the capacity of a capacitor with a multimeter, but there are certain caveats and restrictions to that. To do things properly, you probably want an LCR meter, so that you can measure the capacity at a certain frequency and understand certain other parameters. And then you may specifically need a specific, let's say, ESR or equivalent series resistance meter if you're trying to troubleshoot and see if a capacitor is still working correctly or not. Right, so let's try and understand some of the key fundamentals or basics about a capacitor that kind of affect the amount of charge that it can hold. So as I said, what we're looking at is that you're going to have a positive and a negative charge on these plates. Now, the characteristics that affect the amount of capacity and charge that a capacitor can have will be, for one, the size of the plates, the actual physical size of the plates themselves. Two, it'll be the distance of the plates apart. So you can see there's obviously a certain air gap or distance between them. And then three is the dielectric. So I mentioned air gap. In this case, in this capacitor, the dielectric or insulator is an air gap. But obviously in many other capacitors you'll have either paper, or I said wax, or tantalum, or some other exotic, and that also affects the capacity of a capacitor. Now on this capacitor, which is a variable capacitor, you can see that the overlap of the plates changes. As I turn this round, this will be the kind of one side of the capacitor, and this will be the other side, these plates over here. And as I put them, the surface area that kind of starts intersecting and crossing is going to increase. So in this case, the capacitance is actually going to increase as the plates are folded into each other there, because you've got more cross-sectional area across from each other. And then obviously that is reduced as this comes up. So I must say it's a nice example to see literally a very basic understanding of what a capacitor is, and that is this. Now we'll go have a look at some theory and some analogies. Right, so the first thing to probably perhaps have a look at and understand is that the electronic or electrical symbol for a capacitor is this kind of line with what seem to be like two plates, which is a nice representation because that's exactly what it is. Now you may find that you get an electrolytic capacitor which has got polarity and has to be connected up in a certain way. It's got kind of this more rounded side to it, denoted as the negative side, and the straight plate as the positive. Or just simply a normal capacitor with like these kind of two plates. Sometimes you find them drawn with kind of more rectangles on them. And you may even find, let's say, a polarized or a capacitor with polarity just simply done with the two plates and then a positive and a negative. Now, there are loads of complicated calculations related to capacitors, equations and calculations. So to keep it simple, because if you understand these fundamentals, you'll have enough knowledge to go ahead and go and use capacitors in circuits and understand what they're all about. Certainly once things become more advanced and you do more advanced design, you certainly may want to get down into those more complex equations and calculations. But very basically to understand, so if we have a circuit, so we've got our battery over here with a positive on this side and the negative on this side, we've got a switch in the circuit, and here is our capacitor. And over here is a resistor representing our load. Now once you throw the switch down in the circuit, which is DC, you're going to have a charge, positive charge build up on this side of the plate and a negative build up over here. And basically through this electrostatic charge and the process of ions and electrons changing, that is going to induce, now use the word induce, it's going to allow electricity or current to flow through the wires. And as I stated before, the current actually doesn't flow through the capacitor itself. It's literally just a case of the electrostatic charge changing the ions and the electrons, which then causes the current flow through the wires itself. But for all intents and purposes, for normal convention, you can see it. You can see and understand it and explain that basically the charge does flow through it. But in practical scientific terms, current doesn't physically flow through the capacitor because it has got an insulator or dielectric in the middle. Now if we have a look at our example here, we've got a DC supply going to that capacitor. The interesting thing to understand is that it will build up to the potential or the voltage of your supply over here, and then it's going to stop at that point. So the charge will build up to that point and then the current's going to stop flowing. So if we had to look at a graph of that, as I said, your voltage, when you switch that switch down, your voltage is going to build till it reaches the voltage potential of your supply over here. And what's going to be happening if you had to measure the current flow, let's say through the load, it'll initially start off high as you kind of initially throw that switch, but as that capacitor gets charged, the current flow starts dropping off until the point when it actually starts blocking the current flow. So with DC, a capacitor actually blocks the current flow, and these become the very useful characteristics of a capacitor. With AC, it actually allows current to flow. Now we're going to have a look at an analogy which will hopefully help you understand or give you a better picture. But in terms of a very basic equation to understand is that Q, here I've got Q, positive Q and negative Q, which represents a charge, and then the voltage across the plates of the capacitor. And to understand capacity or capacitance, which is measured in farad or farads, it's Q, the charge, divided by the voltage. Right, so let's go and have a look at that analogy. Right, so we're back to pumps and water pipes again to try and get an analogy to kind of explain the working of a capacitor. So there's a few things to note here. So in this picture, we've obviously got a pipe system. Over here, we've got our power source or our pump. Over here, we've got our valve or stop valve, which acts as resistance to the water flow. Over here, we've got our capacitor. And over here, we've got our load, or the work that's being done to our appliance. Now, here in the representation of a capacitor, if you had to look at a capacitor, let's say this is obviously in a series circuit, it would be like having a container with a couple of bladders. So let's say we've got a bladder on the one side of the container over here and a bladder on the other side of the container over here. And a valve with a kind of float which can potentially go up and block the one side of the capacitor, and likewise a valve on this side. And then what I've got here, these little kind of scribbly bits in between, are what I would call steel wool or Goldilocks, kind of the stuff that you would scour plates or clean plates with, comes into the picture as well. Now if we had to picture that we put on our power source and we've got DC current, so DC is obviously constantly flowing in one direction. What's going to happen in this scenario? The water flow is going to flow, it's going to fill up this bladder, it's going to push, and it's going to, as you can see, it's actually going to push water out the other side and allow current to flow for a while, because what's going to happen, this bladder is going to push over and then it's going to block. This little gate over here or valve is going to block and then stop once the capacitor is full. And that's literally how it works in an electronic circuit. And as you can see, this kind of represents exactly what happens in terms of where I said you don't actually get current passing through. As I said, there's a science and electrostatic charges that happens, but this may give you some understanding that you can actually have flow without current actually physically flowing through the capacitor itself. So there you get your current flow, and then it stops. It then starts blocking the DC or the flow of water or the flow of current. What happens if we have to apply AC, where we've got our alternating current going in two directions, so our pump is going backwards and forwards? Well, then you can quite clearly see that you actually are going to get current flowing through the capacitor, because you're going to have the pump going this way, which will obviously allow, you'll see the bladder push current out this way, and then as the direction changes, it's going to flow back this way. The bellows is going to push out this way, and you're going to get current flow that way. And it will allow an alternating or a current with frequency going back and forth to flow. Now there's a few interesting things to note in this scenario. For one, I've introduced and I've got a resistor here because one of the interesting things about capacitors is the RC time constant. So capacitors can be used as timing devices. So the one thing to note here, particularly whether it's AC or particularly a DC circuit, you can have a certain resistance to the flow of current coming into your capacitor, and as you can realize, if you're going to slow down the current or volume of water coming into the capacitor, it's going to take longer before it actually fills up and then stops and then blocks the DC. And that is something we're going to cover off later, because that's a very useful characteristic of a capacitor. Then we've got these, as I said, this kind of steel wool in here. And what we want to talk about is the theoretical makeup and components that we need to understand go with a capacitor. If we have a theoretical look at the makeup of a capacitor, what we need to include in it is something called ESR, or equivalent series resistance, that it's going to have. It's going to have its own internal resistance as well, and then it's going to have ESL, or an equivalent series inductance. So all of these need to be taken into account because they play a particular role in how it's going to behave under certain conditions. Now, the ESR can be seen as the dielectric loss, and if we have a look at our little analogy over here, these bellows, the kind of space in between the bellows here, which is acting as our dielectric, if you like, that movement or that restriction on the kind of flow of current and what's going on here is going to obviously have an effect on the loss of a capacitor, and that accounts for the ESR. The kind of steel wool over here would account and be like the inductance. That acts as the inductance. So something we need to understand here, all those characteristics are impedance. Now, impedance is the resistance to the flow of electricity under certain conditions, and that in particular is related to frequency. So as, let's say, we've got an AC current flowing back and forth through our capacitor, if we've got this kind of steel wool here, it's got to pass through there. It's going to have a resistance, a certain resistance to the flow of the water going through, plus the water is going to come back. So let's say now the frequency is going to increase and it's going to be going back and forth through a lot quicker. It's going to incur more resistance or impedance because that is related to the frequency of the current going back and forth through the capacitor. So these are the things we want to kind of understand, is that you have parasitic inductance associated with the leads and the electrodes of the capacitor. So how does that affect things in particular when you're applying AC across a capacitor? Well, if you look here down at the diagram, I've got a diagram of impedance, which is obviously the resistance to the flow of electricity versus frequency. So if we start at a low frequency, you're going to potentially get a graph that appears like this, where initially you're going to have high impedance, which then becomes lower to a low point, and then goes up and goes high again. And those of you involved in kind of oscillators or involved in radio will understand that this sweet spot is where what we call the self-resonating frequency. And this is a nice sweet spot to have when we're trying to tune our antennas. Now, the first part of this curve, we have a high impedance, but what's that due to? That is due to dielectric loss. And going back to our analogy, let's say now we've got this kind of bladder over here, which is also acting as our dielectric. So if it's got a stiffness, if you can imagine the frequency of the water pulsing backwards and forwards, slowly is going to have a hard time to move that if it's stiff. So it's got a harder time, so that is playing a part. That is our dielectric, and that's where we're getting our loss. So that accounts for the first part. But as it starts speeding up, that effect starts dropping off because we now got movement. We've got over the inertia of trying to move this thick, let's say this thick bellows or the dielectric. So then we start hitting our sweet spot, where the impedance drops down to a low point, where we, let's say, hit our self-resonating frequency. But then as we start increasing the frequency, impedance starts going up again. What's that due to? And we've said that's due to the inductance on the kind of electrodes or the leads. And that's why I've got, as I said, you've got these inductors, or let's say pretend the steel wool in the pipes here. And of course, as the frequency increases there, although now your dielectric isn't playing a part, you're rushing past the steel wool or Goldilocks inside your pipe, and that is now playing a part in adding resistance to the flow of the water or the electricity through the pipe system. So hopefully that gives you some analogy into understanding of how, giving you a picture of how things work and understanding the various characteristics that need to be accounted for in terms of how a capacitor is going to react under DC and AC. Right, so the next thing we want to have a look at before we get down to a practical demonstration is the RC time constant. And as I said, this is a really important part of the capacitor because this is, for one, as I said, the kind of timing, the time usage of a capacitor is very useful, but this also helps us understand and work out the capacity of a capacitor. So if we have a look at this graph over here, we've got voltage on the Y scale over here, and we've got time on the X axis over here. And if we kind of apply that DC voltage to the capacitor and let it charge up, as I said, what you're going to see the voltage climb to the to be equal to the supplied voltage from your source, whether it's a battery or a power supply or what have you. So as that climbs up, it's going to take a certain amount of time. Now, this is very useful because understanding that curve and the time it takes to build up will help us calculate the capacity of a capacitor. Now, there are a few things to understand how this is derived. Now, the calculation that's actually used is taken from, and we'll do this on the oscilloscope, is taken from a certain time point, which is known as a time constant. Now, the complete time taken for the capacitor to charge is actually taken over or divided into 5 time constants. So you've got 5 of those time constants, but you only need to use the first time constant to be able to do the calculation to work out the capacity. Now the point, the time, to understand what the time is, so you take the charge time. So once your charge gets to 63.2% up your curve, that is where you take your time constant from. Now, where does that figure come from? That is derived from the natural constant E. So in mathematics, you've got certain constants. You've got pi, which probably all of you know about. And there's another one, a very important one, called E. Now, if you in fact go to your calculator and go 1 minus 1 over E, you will see you get 0.632 something. And that is where that is actually derived from. So it's certainly not sucked from thin air. And this E is naturally occurring in process step response. So if you go and plot population growth or interest on money or radiation decay, there is a natural constant which occurs which describes the growth and the end of the growth, and that is related to E. So that's where it comes from, and we've got this kind of step progression or growth here, and that's why it relates to the timing of capacitors as well. So if we take then the capacity of a capacitor is equal to time, and that's the first time period, divided by the resistance, we will then get a capacity in farad. If you want to work out the total charge time of a capacitor, which can be very useful in kind of working out for a timing device in a circuit or what have you, then time total would be equal to the resistance times the capacitance times 5, because you've obviously got 5 of those intervals. And just to give you a little example, let's say we've got a circuit over here, and in this circuit we've got a 240 nanofarad capacitor, and we've got a 146 kilo ohm resistor, and you wanted to work out how long, if you apply a charge to that, how long it takes for the capacitor to charge up. Well, then you'd say your time total is equal to 274 to the exponential of minus 12, because it's nano, multiplied by your 146 raised to the exponential 3, because it's kilo ohm. That first answer will approximate, not exactly, but it will be around 40 microseconds. If you multiply that by 5, you will then get approximately 200 microseconds, and that would give you the charge time of your capacitor. Now, another important thing to note, and this especially comes down to kind of understanding how the measuring tools work out. They only need that first time period to work out the capacity of a capacitor. And something interesting to note is that often capacitors in use won't obviously fully charge and fully discharge. Most of their work is actually done in this first period, for the most part. There are obviously caveats to that, but if you're not fully charging a capacitor and it's in an AC mode, a lot of its work life will actually be spent down in this area over here. Let's go and have a look at a practical demonstration. So what I want to show in this next demonstration is, for one, to show you this charge curve. And what we do, if we go and have a look back here at these curves, What I want to demonstrate is obviously this charge curve as the voltage builds with a DC load, and how the current initially starts off high and then drops off, and then current flow is blocked. So that we'll do a demonstration on now. Right, so we're ready to do the practical demonstration. What we're going to do, as I said, I've got an electrolytic capacitor here. I've got an oscilloscope which is going to measure the voltage. My Rigol bench meter up there is going to measure the current, and then I've got a resistor in the circuit as well. And I've got a signal generator which is going to provide a DC signal going, or DC charge going into the capacitor. So in very simple terms, this is what the circuit diagram looks like. The resistor, I'll explain, so that's to control the charge rate of the capacitor. We don't want it charging up too quickly, or else we don't get to see that nice curve. So that controls the charge going into the capacitor. We've then got the bench multimeter acting as an ammeter to measure the current flowing in the circuit. That's the capacitor which is being charged up, and across that I'm measuring the voltage with the oscilloscope to see the curve and how it climbs up. Right then, so I've got everything set up. I've got the oscilloscope at the top and I've got the Rigol at the bottom to measure the current. And it's got it trending, and at the moment it's noisy because it's measuring kind of very low amps and making a noise. Once we get some current flowing through there, that'll clear up. So what's going to happen is we're obviously going to pass a DC current in, and then I'm going to switch that off. And what's going to happen when it's going to switch off? So initially we obviously expect to see the voltage climb like this. The current's going to start high and then dip off. And then when we switch off, well, things are going to push the other way because we've got this, remember, we've kind of got this bladder. So if we remove the voltage, remove the pressure, it's going to push back. So let's see how that happens in practice. So right, so if you watch the oscilloscope, I switch it on. There we get our nice curve building up through the capacitor. And on this down here, you can see, there we go, there was our current. It started off high and then it's dropped off, and now we've reached the peak of the charge inside the capacitor, and the current has now basically stopped flowing. And if I then go and switch that off, we can see the charge now being removed, obviously through the load. So it's got that nice curve coming down, and you can see the current has flowed in the opposite direction, negative, because it's pushed out of the capacitor, started high, it then curved up and went back in. So I'll just do that one more time. There we go, we get our charge up. And now what I'm going to do, I'm just going to stop that there. And this is that curve. So we're getting this nice curve because we've got the resistance in place to control the rate at which the current's flowing into the capacitor. So we do get this nice curve. And I said what we're going to show in a later video is how we can then take a measurement to actually, we're using an oscilloscope to actually measure the capacity of a capacitor. Let's start that again. So there we go, it's already charged up. We'll let it discharge. So you can see that curve coming down. And again, the current is now pushing out, it's gone negative, and we'll do it again. Just one more time. Voltage going up, building, and you can see likewise what the current's done there. And that obviously represents these curves that we've got here. Right, so next we're going to move on to doing experiments and doing a demonstration using AC. So not DC, we're going to show AC going through the capacitor and how it reacts.